So now that we have looked at the hypothesis testing procedure for an ANOVA test and what it is like to check the conditions, let's go ahead and put some of that into practice with an example. So this says, a researcher wants to determine if the average amount of time needed to eliminate a headache is different for aspirin versus ibuprofen versus acetaminophen versus a placebo. So notice right here, we're going to definitely have to use an ANOVA test versus the other type of tests we've learned because we have more than two groups to compare. We have aspirin, we have ibuprofen, acetaminophen, and a placebo. So we have 4 different groups to compare. The researcher randomly selects patients for a study and divides them into 4 groups of 50 patients each, and each group is administered a different medication. Assume the populations are normally distributed and have equal variances. Okay, so first we want to determine if the conditions for conducting an ANOVA test are met, and then we want to write the null and the alternate. Okay, so let's look at the conditions. So to answer part A, then I'm going to write number 1 down. It says each population from which a sample is taken is assumed to be normal. Well, that is given to us in this information. Assume that the populations are normally distributed. So assume populations are normal. That was said. I'm going to go ahead and skip to 3 just because it's in that same sentence because it says assume the populations are normally distributed and have equal variances. So it's also assumed equal variances. Okay. Number 2 condition says the samples must be randomly selected and independent from each other. So it does say the researcher randomly selects patients and divides them into 4 groups of 50 patients each. So there is random selection, and these groups appear to be independent of each other. There's no reason to think that there's anyone maybe related to each other in these groups or anything like that, because if they're randomly selecting the patients and putting them in these groups, everything also appears to be independent. So it looks like random and independent is also check. So let's see. 4 is that the input variable has to be categorical, and 5 is that the response variable has to be numerical. So let's see, what are the input and the output variables, and do they fit these definitions? So we want to see the input then here would be the categories, right? The aspirin, ibuprofen, acetaminophen versus placebo. So that's the type of medicine, which is categorical. Okay. And the output, what are we checking out about this type of medicine? We're checking out the average time to eliminate a headache. To eliminate a headache. So that is numerical. So we do hit all of these conditions. So all the conditions are met. We can set up an ANOVA test for this. So part B then says, go ahead and write your null and your alternate hypotheses. So remember, you can write your null hypotheses 2 different ways, and you can write your alternate hypotheses 2 different ways. So let's practice both of them. The first way to write your null is to say that there is no association between this categorical and numerical variable. So I could say something like, there is no association between medicine type and average time to eliminate a headache. But those things are not related. The other way to write the null hypothesis is to say that the average time for each one of these medications is the same. So I could say that the mu, the population mean of, let's say, aspirin, is the same as the average for ibuprofen, is the same as the average for acetaminophen, which is the same as the average mu of the placebo. So you don't always have to write both of those. Those are just two different options. Now, there are two different ways we could write the alternate. The more wordy way is to say then, if we're assuming in the null that there's no association, then the alternate would be that there is an association. So I can say there is an association between medicine type and average time to eliminate a headache. Okay, yeah, those get a little wordy, but we could say that. And the other version of the alternate is to simply say at least one of these, and I'm going to be a little bit more specific. I'm going to say mean times is different. They don't all have to be different. So what you would not want to do here, so, or I should make a big red X. What you definitely do not want to say as an alternate is something like this, that the mu of the first is not equal to the mu of the second, is not equal to the mu of the third, is not equal to the mu of the fourth. That is not what we want to say. We don't need to show that they're all different. Cross that out. We only need to show that one of them is different. Maybe they are all different, but only even just one of them being different would be enough to say that there is some kind of an association here. We may not know quite what it is, but if one of those means is different, then we know that there's something interesting going on. Okay, so just be careful. This is something that students want to use as an alternate a lot of times, and it's just not an okay way to write it. A little bit more information on ANOVA testing. The distribution used for an ANOVA test is called an F distribution, and it has an F statistic. The F is calculated by taking the variation between the groups and dividing that by the variation within the groups. Unlike the normal and T distributions that we've studied in the past, the F distribution allows for only positive values. It's usually not symmetric. It's actually typically right skewed. So it has like the hump on the left and the tail extending to the right. When you're finding the p-value, you always use the area to the right of the observed test statistic. So there is no option for like above or below in these because there's no negativity. It's always just to the right. If the variation between the groups, so that's your numerator, if that is large compared to the variation within the groups, then F will tend to be large, because what that's doing is giving you a larger numerator and a smaller denominator, and that makes a large value overall. A large F test statistic discredits the null hypothesis of no association. So when that F value is large, that discredits the null, that's going to result in a reject the null situation. So a test statistic and F statistic being very large will mean that it's very, very far out here to the right. And that's where your F statistic is. The p-value then beyond that is the area to the right of that. So the p will end up being small. And we already know that the small p-values lead to rejecting the null. Then on the flip side of that, if the variation between the groups, the numerator, is small compared to the variation within the groups, the denominator, then f will tend to be small. If you have a small numerator and a large denominator, then that creates a small number. This would follow the null hypothesis of no association, and this would lead to a fail to reject H sub naught situation. So again, in the visual representation, a small f value would be very far over here, let's say to the left, meaning that there is a lot of area underneath this curve to the right. A large P would be associated to that, and we again know from prior information that large P values lead to failing to reject the null.